Ken is up now. Ken, introduce yourself and
Hi there.
the show.
I'm Ken Boak. You can probably tell from my accent that I'm from good old Blighty. Um, I did a presentation to Fourth 2020 2 weeks ago, and rather than give you that exact same presentation, because I know some of you may have seen it, um, I've recrafted it.
Forgive me, Ken. Let me quickly ask you, is that talk available online? Could we
Yeah,
watch a
the
rerun?
last the one from 2 weeks ago is online. Will I will put a link in the comments at the end, if that's okay. Right. So I shall begin sharing my screen and I think it's probably this one. Could someone confirm that they're seeing um, a title page with
I
a
just see
bowl of
your
mint?
face right now. Just your
Oh,
face.
no. Sorry. Um, Hit the wrong one. How about that?
Now we see Ken has started sharing, and then we see mint, a seed to grow forth.
Right. Okay. Um, but are you seeing the sidebars of my presentation? No?
No, we just
Just
see a like
I
a
just the
don't see a
screen.
PowerPoint
phone.
screen
Okay,
with
that's
no
perfect.
sidebars or index or
Right.
other
Perfect.
extraneous.
Okay, so let me let me try and introduce the concept of mint in the first half dozen slides. Um, Something that got me interested about the mechanics of
Ken,
fourth. Yeah.
there's a gray bar at the top of your screen that is blocking the title.
Oh, this meeting is being recorded. Sorry. That's it. Gone? Has
Gone.
it gone?
Thank you.
Right. Sorry. Okay. So about 8 years ago, our German colleague Ulrich Hoffmann um, wrote a paper for Eurofourth about a new synthesis for fourth, effectively starting off with a small kernel and then extending it to the point that it would become a fully fledged fourth with a couple of hundred words. So that got me interested in looking at the mechanics of fourth. And I'd read a bit by our colleagues, Chuck and Ting and um, Jeff Fox and others. And it became clear that, uh, and unsurprising really, because they had quite a lot of uh, uh, sharing of information and ideas between themselves that Ting's E4th, the primitives used in that went on and were almost adapted universally as the single opcode instructions in the range of the various fourth engines, starting with the MUP 21 and ultimately the Green Array's F18A. So um, that that was an interesting fact. So um, I decided that I wanted to produce a lightweight cousin or younger cousin to fourth. And this is where the idea of MINT arose from. So MINT is a portmanteau of minimal interpreter. It's an interpreted stack-based integer arithmetic RPN language. So apart from it being purely interpreted, all of those are in common with regular fourth. It uses data stack and return stack, but here's where it becomes very minimal in that it just uses the printable ASCII characters as words, variables, and primitives. So of these, many of the symbols that I've chosen will be very familiar to fourth users. For example, fetch and store are the @ and the exclamation mark. And the arithmetic words, they just use the regular mathematical symbols. And so from the 30 or so printable punctuation and arithmetic symbols, you can build up unique codes that represent the bulk of the E4 primitives. So the next major difference, there's no dictionary, and the words are accessed using a very simple jump table. And it provides a subset of fourth, which I intended for very lightweight applications where the processor that you may use only has very small ROM and RAM space. The source code, although it is very compact or terse, it does actually have quite a good degree of human readability. And in terms of writing it, you really only need a serial terminal, and you can cut and paste code straight in to the target board from the terminal emulator. So myself and a couple of colleagues, we went on to write a MINT interpreter for the Z80, and it came in at about 1,700 bytes. So clearly it's very compact. So moving on, the MINT virtual machine, it can be hosted on virtually any CPU. Like I say, there are 31 primitive operations which can be accessed using an 8-bit jump table. And you have the usual support routines for character strings and decimal and hex handling and number input and output and number conversion and serial comms over a UART. So apart from that, there's not much more to it. The variables are 16-bit and they're represented by lowercase characters A through to Z. The uppercase words to call the user routines, they are the capital letters A through to Z. And then you've got memory access with the familiar fetch and store. There are special characters used for the stack operations. You've got the arithmetic, logical, and shift operations, and a way of indicating what's a hex number. And the stack ops, as I mentioned, you've got dupe, which is a duplicated comma, or should I say quotation mark. Drop drops one of them. Swap looks like a capital S, and over looks like two things have been swapped over. And then finally, the / character that can precede any other character, and it provides an extended function which could possibly be accessed by an extension jump table. So putting that together, there we have the list of MINT operators and what they all do. And then a little bit of history. A Japanese gentleman wrote a tiny fourth about 20 years ago, which gave this similar concept, tiny basic, where you've got 26 variables and a reduced command word set. A later development, Ward Cunningham wrote a tiny interpreter to run on an Arduino with only 13 commands, one variable X, no arithmetic, no stacks, and no colon defs. But it provided an immediate means to access the C routines that controls the Arduino GPIO and ADC converters and all the other I/O. So I came across that about a dozen years ago, and I ported it to MSP 430 because I wanted a 16-bit target. And I called it Simple, which is Serial Interpreted Minimal Programming Language. And over the course of some evolutionary steps, I added maths, user-defined colon definitions, more variables, and I used it as a general purpose tool for testing hardware without having to go through the usual compile, find a bug, edit, compile. So it gave quite a rapid way of being able to try very quick things out on prototype hardware. So I sort of referred to Simple as a hardware bring-up tool. So from there, Simple got ported to a whole host of other Arduino boards. It still didn't have proper stacks, but colon definitions could be chained together to form new functions. It was at that stage that I ported it to MSP 430 assembly language, having come across Ting's E4 code for the MSP 430. And then about 5 years ago, I decided that I had to bite the bullet and get the missing stacks properly working. Motivated by some presentations that John Hardy from Melbourne had given. So I rewrote simple in Z80 assembly language for my my little single board computer. So in the spring of 2021, I got chatting to John, and I heard of a language by a Hungarian gentleman called Stable, and it was a minimum interpreted bytecode language written in C, but the main thing is that it formally defined in C code um, uh, how to implement the stacks. So I used that as a model, and I then went on to get together with uh, John and one of his colleagues during lockdown one, and John wanted to use eMINT as an alternative to typing hex codes into a very early Z80 machine that he'd developed some 40 years earlier for an electronics magazine called Talking Electronics, mostly published in Australia. The Tech one was a typical trainer, just with a hex keypad and 7-segment hex displays. And so it was advantageous to use eMINT as a slightly higher level language that could be entered from a terminal program. And to accompany that, Craig Jones, one of John's colleagues, he provided serial bit banging code for the Tech one, and also a Intel hex loader. So by the time we got to Christmas of 2021, eMINT was more or less demonstrable, and people could start trying it. So also running in parallel with that, Jason Tay produced a generic version of eMINT that was written in C, known as cMINT, and that was ported to a whole host of other processors. So here we've got various different processors. We've got what they're being clocked at, how many clocks they take to do an iteration of an empty loop, and how many iterations they can do per second. Now, up at the top there is the STM32H743, which I later found out is not only has it got a relatively high clock for a microcontroller, but it's also got a double execution unit. So it could go through instructions roughly twice as fast as the nearest opposition. Which would be the one below it, the SciPede, which is a RISC-V. And then down towards the bottom, there's the humble Arduino at about 200,000 operations, empty loops per second. And then the poor old 8052, which comes in at about 1/7 of that. So that shows the spread of what's achievable on various processors. So here's a picture of the Tech one, as first published back in 1985. They liked big boards back in those days, and they didn't have much much idea about ergonomics. I wouldn't like to be a left-handed person using that board. So this is this is one variant of the RC 2014. The first one, which there are very few chips on each of the plug-in boards, but it's a reliable machine and not terribly expensive. So extending Mint. I said that we reserve the / character as a means to extend the language. Now that could either, as I say, select a different jump table, and that could be just as easy as setting bit 7 of the ASCII character high, which instantly gives you another 128 possible bytecodes, not all of them visible, depending on the video circuitry of the particular machine being used as the target. I remember back in the early days that the characters with bit 7 set tended to be displayed in inverse video, which is sort of like color forth for monochrome displays. So using the hashtag could also be used to provide longer words for the functional names. So you could start a word with a / and end it with a /, and that would be considered to be just one word, like DUP for dupe. Now that might make it more verbose and easier to read, certainly for the source code, but it would be possible to use perhaps some sort of a Python script that would reduce the verbose version down to the minimalist version for sending over a UART or SPI link to the target processor. So the other 2 points I've already covered. I said that Mint was early adopted by the Tech One community, which is still quite a vibrant group on Facebook, especially down in Australia and New Zealand. John Hardy went on to extend the Z80 version, which he calls Mint X. And I'm slowly working towards a CPU design using 74HC CMOS logic and possibly an FPGA that will execute Mint as its native assembly language. And that's something I'm calling the Mint machine as a working title. There I say that Mint's got a very limited symbol set, could use Python or C++ to help automate the build of Mint for a wide range of target MCUs. As long as they've got the Mint primitives, it makes it very easy to port from one processor to another. Okay. How am I doing for time, Kevin?
You are fine for time.
Okay. Sorry, I didn't check
the
clock.
15 or 20.
Okay.
Otherwise,
It won't be that long. So, if any of you have seen the Quentin Tarantino movie Dusk to Dawn, which starts out as a nice, peaceful story about a family traveling into Mexico on some sort of a religious mission, and then somewhere in the middle of the film, it turns into a zombie infested bloodbath in true Tarantino style. Well, when you try and graft a presentation together, that can sometimes be the result. So anyway, I having given that presentation a couple of weeks ago, I got more interested in Ting's E4th model, and I decided that I'd code up the mint primitives so that they follow the same function as the E4th primitives, and so what I'm working on now is a means to use this slightly different version of Mint, which I might call eMINT, to create this sort of kernel that can be extended and converted into a fully fledged fourth. So that's what I'm doing at the moment. Now, there has been various prior art to this. There are at least two that I've found. There's Sector Fourth, and it's either Mini Fourth or Min Fourth. They're intended, well, Sector Fourth was intended to go into the 510 available bytes on a disk boot sector, and then be able to synthesize the full set of fourth words from this reduced set of primitives. But my inspiration, as I said, has come from the instruction set that Chuck and Ting worked on in the mid 1990s, and I believe on Complang in about 1996, Bernd Paysan, he suggested that you could probably get away with about 13 primitives and still write something that executed a reasonably efficient fourth. But fewer than 13, and there have been some attempts, mean that almost every word is made by concatenating primitives. And so you've got the repeated time overhead of having to execute next in the inner interpreter to handle all these concatenated primitives. So the fewer primitives you use, the slower the language comes. And some of you will know another esoteric language often referred to as brain fuddle, amongst other things, and that uses only about 6 characters, and simple programs run to hundreds of characters because you just can't get anything done with such a low quantity of primitives. So on the Z80, the 30 or so primitives fitted into just about 200 bytes of assembler. It's a bit more, well, it's roughly double on the 6502 because you have to do a lot of zero-page memory operations, and you don't have access to some of the 16-bit register-to-register math operations. But again, lifting a page from Chuck's notebook, with 31 primitives, you can code them up in a 5-bit opcode. And like the MOP21 and then Ting's P16, you can take several of these 5-bit opcodes and pack them into, in this case, it would be a 16-bit word. And I've recently managed to get some of these primitives tested on my Agon Lite 2, which is a very fast single board computer based on the enhanced Z80. So just to tell you, or rather show you how minimal sector fourth was, there are 10 primitives there. And having if you've only got SPAT and RPAT, the simple stack operations, dupe, drop, swap, and over, they start to become very verbose. And I'm a firm believer in maintaining the stack ops as primitives, because in conventional fourth, you are using them so often. Here's the Agon Lite. It's quite a small board. It's in inches, it's about 5 by 3.5 or so. So that's roughly twice scale in that image. Well, it is on my screen. But what's nice about is the price, about $55 US. So here's your Easy 80, which is basically a pipeline Z80, which can execute many of the Z80 instructions in a single clock cycle. And it also has a set of what we refer to as modern peripherals. So there's SPI, there's 2 UARTs, there's a DMA controller on chip, and timers on chip, and 8K of tightly coupled RAM, and quite a substantial sized flash memory. You've got 512K of RAM, a micro SD there that you can put up to a 32 gigabyte micro SD in. And this, if you look carefully, that's an ESP32, and that is actually acting as the video display processor. So that's taking in fairly high bandwidth serial from the Easy 80 and converting it through a series of resistor networks into VGA. 2-channel audio, power and communications from USB-C. And then you've got this quite comprehensive GPIO bus coming out the bottom of the board. And you can battery power this. It takes about 300 milliamps or so. So it's quite frugal. Right. I'm just going to finish off with something that occurred to me. We've had tiny acorns turning into oak trees, and now I'm going to talk about Lego. So Lego provides basic creative building blocks, just like Forth. It's been around since 1958 in its current form, which coincides with some of Forth's early beginnings. And many of you will have had Lego as a child or as a grandparent, a parent, and it certainly starts the creative mind working from building things from basically what are just a series of standard sized blocks. The quote in italics that came from one of the Lego managers many years ago, saying that there was a system that they adopted at Lego, which meant that it didn't matter whether you bought Lego 50, 60 years ago or brand new, it will still fit together. So in Lego, we've obviously got bricks, and there are a limited number of standard bricks. About 15 in this case. And what's interesting is that you can build up larger bricks by putting some of these together. You can put them lengthways and make longer, or you can put them side by side and make wider. So this sort of is reminiscent of your coded up primitives in assembly language. They might be one instruction long, or they might take 2 or 3 bytes or even more to code a primitive into the native assembly language of your processor. So think of the little round studs on the top as being the equivalent of an assembly language instruction. And looking at the 1x16 here, I can put my hand on my heart and say that none of the Z80 primitives exceed 1x16. So here's what I've tried to indicate in the previous slide. We only need somewhere between 16 and 32 primitives, and we can make those quite easily from a very small set of building blocks. So the ultimate aim of the minimal instruction set computer is to reduce each primitive to a single instruction in the native assembly and have it execute in a single clock cycle. So that is that's the crock gold at the end of the rainbow. So future work, I mentioned the eMINT machine. Just a few stakes in the ground of some of the things, the direction of travel I'm heading in. And I think it's almost demo time. Right. Here's an example of some eMINT code. What I'll do is I will demo this on my Z80 system. So I will swap over to my terminal emulator. Do you see that? Maybe I need to share a different screen. Just a sec.
Sorry, I did see a terminal emulator there for a sec.
Okay, is it?
There's the terminal emulator is back.
Okay, great. Okay, so hopefully in the last hour or so this hasn't crashed. So eMINT Sorry. Start again. Right. Mint's located at 8,000 in hex in the RAM on the Z80, and you can tell it's sorry. I do apologize. Let me see if I can make this pesky thing work again. This was working perfectly.
That's the traditional approach. Have it die right in the middle of when you're presenting it.
Right. Okay. Hopefully we're hot to trot. So we do a go 8,000. Remembering to click on the screen that I'm actually working on. And we come up with Mint. And then this is not looking good. I think what I'll do, I will go and fix this, and if there's some spare time at the end of the meeting, I will demo it then, if that's okay.
Yeah, okay. Bob Armstrong will have to decide that. If you communicate with him. If you don't want to do it this month, you're welcome back next month to give us a little quickie. We'd be pleased to see it.
Can you answer a few questions?
Yeah, sure. I shall do my best. Just a sec.
Can you go back to that board that I saw? The argon
Yeah. The argon, yeah. Great. There we go. Yeah. I will put a link up for that in the comments. In fact, all of my links will be copied into the comments.
So did you create the eMINT?
It's a work in progress. I've got the primitives written, and I just need to put the glue around them.
Is what you have up on GitHub?
Yes, it is. I'll point you to that. Are you flying?
Do you have a slide? Do you have a slide with your contact information and links?
Yes, I will do that. Yeah.
Thank you for all your work so far. I hope to see the glue.
Okay. Well, I have to credit my teammates on this project. It wasn't all mine, and John and Craig and Jason and others, as well as the inspiration for it from the likes of Chuck and Dr. Ting. It certainly gave me an interesting project.
Once again, thank you.
Yeah, just let me share the correct screen this time. And I hope the audio is a bit better. I hadn't got my headset plugged in for the first bit. Okay,
We
so
can hear you just fine.
right, and you've got the terminal screen. Okay,
Terminal
so
screen is up on ours.
we know it's a fourth because we can do something like this, which I hope most of you will recognize. And due to minimal reasons, I haven't suppressed the leading zeros. But the thing is, white space is only required to delimit numbers. So that could be written like that, and you'll get the same answer, obviously. Right. So I've got some pre-prepared words in there. So um, I'll show you this one. So I've got the letters of the alphabet coded up, and when it sees a one, it emits a inverse space, and when it sees a zero, it emits a space. I can show you the code for that. I've got another one up my sleeve, so that's mint. You may wonder why banana bandana. Well, it only needs B's, A's, N's, and the occasional D. So less letters to code up. If you want to make a change to the to anything, supposing I don't like the word mint and I want to make it Ming. What I can do is I can paste with carriage return, and here is the string for mint, and I've changed the last T to a G. I've given it the user word name M, starts with a colon, ends with a semicolon. You paste that in, and that's it. And now if I type C, which is the word that calls it, there we have Ming. So it's that easy to paste. And then finally, what I'll do is I'll just paste the original source code in. So clear the screen, paste with carriage return. This is the original source. There it's going in somewhat slowly. So the first few lines are the arrays with all the letters coded up. Here is the one that emits character 219, which is the inverse space, or it emits the space depending on the value that it takes out of the array. P is for printing that up. It basically reads through the array and does a left shift and feeds the relative bit of the character in so it gets printed. M defines the word, sticks it all together in a string, as does K for banana bandana. And then finally, B and C will print them out. So if I concatenate B and C, it will do that. And if I give it a load of B's, there you go. So that's all, folks.
Okay, we're a little bit late, so we're gonna ask if anybody has something that can't wait till next month. Say it now. Okay, that was good. Now we're gonna pull a plug on the recorder and say goodbye till next month. Thank you so much, all of you.